Hello, everyone. My name is Andrei Marinica. I'm a core developer at Elrond Network. We are trying to be the internet scale blockchain, highly scalable, highly accessible to everyone. And first of all, thank you very much for the invitation. Today, I would like to share with all of you the story of Elrond and especially the story of our VM. How we got from having basically nothing 2 years ago to having a functional VM and on a functional blockchain that we used to run a lot of smart contracts on, and hopefully even more in the future. So with that, I will begin. This is the Elrond WebAssembly story. I will talk about 4 main things. I will first give an overview of what Elrond is and what we do at Elrond. Then I will talk a little bit about how our smart contract architecture is, how we think of smart contracts, and from a very, very high level perspective. And then I will dive a little bit deeper into how we execute them and how we really integrated WebAssembly into our stack. And of course, the last thing, I'll have a really short slide, but very, very important about how we verify the correctness of what we build and what our developers build. So without further ado, what is Elrond? Elrond is a very, very scalable layer 1 blockchain protocol, which many of you might have heard of. We do state sharding and proof of stake. We managed to scale in a testnet. We managed over 200,000 transactions per second, but that's not the most important part. The most important part is that we can technically scale indefinitely with demand. We have a 6-second latency block and very, very cheap transactions. But even more important than that, we have the DeFi, Elrond's money and DeFi app, which is called Mayar, which is a smartphone application that allows anybody with a smartphone access to the world of DeFi and the world of crypto. And so far, it's been having quite some success. And last but not least, we have quite some interesting token economics, our token eGold. I won't go into very much detail about it, but I'll just mention on the fly that it has a limited supply and a very interesting minting and burning model. There's more on our website. This presentation isn't about it, so I'll just move on. Right. Our main innovations. There's a few pillars that make Elrond what it is and that brought us where we are today. The most important one is adaptive state sharding. It's our flavor of proof of stake sharding. There are 3 types of blockchain sharding, and we do all 3 of them. One is a state. So each shard has completely separate state from the other. The other one is transactions. So each shard processes its own transactions independent of the others. And the third one is network sharding, in which the networks themselves don't communicate too much so as to optimize the throughput. Currently, we have 1 meta chain and 3 execution shards, but in principle, we can have more of those if there is demand, or fewer. You know, as the demand fluctuates, we can adapt our number of shards. Then the second pillar is secure proof of stake. This is a special flavor of proof of stake. It's based on a Byzantine fault tolerance, like the consensus mechanism, which samples a consensus group with every round. And we have validators randomly shuffled between shards so that shard takeovers are very difficult. And we also have an unbiasable randomness source, which can be very useful for certain types of contracts. Then we have smart accounts. Now, smart accounts, basically any account on Elrond is a smart account. User accounts and smart contracts are not that different in that they both have an individual data tree where there's storage. Now, of course, a user cannot write anything they want in their own storage, but this storage can be used by the protocol to enable all kinds of cool functionality. And last but not least, we have a thing called custom tokens. We call it ESDT, that is for Elrond Standard Digital Tokens. These are native tokens. So unlike what you see on Ethereum or similar blockchains where tokens are encoded in an ERC20 kind of smart contract, so where all custom tokens live in a smart contract, we decided to build them directly into the protocol. And this is very cool and very important because it allows us to transfer them very cheaply and it's a bit easier to work with them cross-shard, which I'll get back to later. And of course, they are come in 3 flavors: fungible, semi-fungible, and non-fungible, which means we have basically NFTs baked directly into the protocol. Okay, now a little bit about how the last 2 or 3 years have been. A few highlights. We've had the mainnet launch a little more than a year ago. It was late July. So the mainnet has been online for a year now, and without interruptions, that is, which we are very, very proud of. And also in January, we had our Maya launch. Maya, again, is our smartphone app, which enables anybody to connect to the blockchain. It's very friendly. And we're in our final preparations to launch our first decentralized exchange called the Maya DEX, which will be soon, hopefully very soon. There's more about the roadmap and the projects we do on our website. There will be a launch pad, there will be an NFT marketplace, a lot of cool stuff coming, but this is just like the major things. Now, I gave you a little bit of an introduction of what Elrond is, and now I want to really start telling the story of how we came about to building our smart contract infrastructure. Now, the first and major obstacle, the major challenge that any sharded blockchain has is how do you run smart contracts in a sharded architecture? Because as I mentioned earlier, the state is completely separate. So each shard has its separate state and they're separate transactions, which means contracts cannot communicate directly across shards, because that would contradict the entire concept of sharding. So each user account lives in a shard, each smart contract lives in a shard, and they all have their own data trees, and then they rely on the protocol to resolve the cross-shard calls. Now, as you can imagine, there's cross-shard calls from users to smart contracts, but there's also cross-shard calls from smart contracts to other smart contracts. Right. So again, shards don't have direct access to each other's state. So how do we do? Now, there's 2 ways we go about this. Of course, as a simple way, similar to what you have on single sharded architectures like Ethereum. We call them synchronous calls, in that if and only if you know for certain that 2 contracts are in the same shard, then of course they can interact with each other in a classical way that everybody understands. So a contract A can call another contract B in the same shard, and the 2 transactions they happen atomically, and you can get the result instantly, which means you can interrogate, you can do all kinds of stuff, and if one fails, then all of them fail. But the problem is, of course, this is not scalable. So we usually prefer not doing this. We do it, but rarely. What we prefer to do is working with so-called asynchronous calls. Now, these asynchronous calls are shard agnostic, which means the developer doesn't care and shouldn't even know whether or not the 2 contracts are in the same shard or not. Remember, I said we have adaptive state sharding. So at some point, the shard might split into 2. So we don't even know. Maybe today, the contracts are in the same shard, but maybe on another day, the contracts end up in 2 different shards. So this is why it's important that we have a mechanism that works in both cases identically. It consumes the same amount of gas, even though, of course, doing things cross-shard is usually a bit slower. And we also can't have the answer. So if you want to interrogate another contract, which is in another shard, of course, you can't have your answer immediately because the data is not there. Now, what happens is you create this kind of transaction to the other shard, and then you wait, and maybe 1-2 more blocks down the line, you will get back the result in what we call a callback transaction. So you get the answer a bit later. And this is not atomic, unfortunately. So the developer has to handle the rollback explicitly in case of failure, or commit things that can only be committed when there's confirmation that the other transaction also happened. And I have a nice diagram here. Now, this, I have to caution you, is the absolute simplest cross-shard transaction from a smart contract to another smart contract. Of course, there's a lot more complex scenarios that can be had. But yeah, in its most simplest form, you have a user. The user is calling a smart contract. Of course, as part of a decentralized application. And contract A needs something done in contract B, which is perhaps in another shard, perhaps not. So what happens is contract A sends this asynchronous call to contract B, and then contract B does its thing, and contract B sends the reply back. This happens automatically, so the developer doesn't have to do that. The protocol always sends a callback back. And if contract B ran successfully, then contract A will know this and will get the answer and will be able to commit stuff. And if contract B failed, then contract A will be notified that, hey, contract B failed and maybe you want to roll back some stuff and so forth. So this is, in a nutshell, how it works. It's conceptually not very complicated, but, you know, as the scenarios become more and more complex, so does the system. Now, the second, so to say, complication, the second innovation is that smart contracts have to interact with ESDT tokens. So I mentioned ESDT tokens earlier. They are native, so they're part of the protocol, and they get transferred just like the native currency. And their ownership is actually not stored in a smart contract, as we're used to from Ethereum and ERC20. They're actually stored in the individual trees of the users. This is very important in a sharded architecture. Just imagine what would mean to run an ERC20 in a sharded architecture. You might be in a shard, and your token might be in another shard. So it would take a lot of time for you even to do the most basic stuff with your token, because you wouldn't have direct access to it. In this way, we make sure that every user has direct access at all times to their tokens, because their tokens are in their account. They're not in a smart contract. So this is, again, what we use these individual account trees for, or one of the things. And another very nice thing that we have is we don't need allowance. Maybe you know, ERC20 contracts have you need to allow other smart contracts to take your tokens from you before you can interact with them. Because we store these tokens with the users. Whenever a user wants to interact with a smart contract, it just sends the contract, its tokens, in one single transaction. So there's no need for multiple transactions there, which again is nice because it makes interaction with the decentralized application world a bit easier. Now, of course, they're fungible, and there's also semi-fungible and non-fungible. And these guys, non-fungible and semi-fungible ones, they carry additional information. Which again, I'll come back to a bit later. And another cool thing that we've had for a month or two is we can transfer multiple tokens at once. So in the same transaction, you can actually send multiple tokens, which is cool from user to user, but it's especially cool if you want to interact with, for instance, with a decentralized exchange, where you might want to swap two tokens. So you might want to send them both at once, and then you get two tokens in return. Right, so as I mentioned, smart contracts can receive and they can send ESDT tokens to. And another nice quirk about this, especially in the sharded context, is the fact that because these tokens can hold data, they can also be used as a form of alternative storage. And now, of course, any smart contract has its own storage, and they can keep that storage, and it's there indefinitely in their own shard, in their own account tree. But let's say you run a multitude of smart contracts that communicate with each other across shards, and you want to share some information between them. Another way you can share information between them, you can have them exchange these tokens, which might not be valuable. They might be, you know, they might not be, you know, the kind of tokens that, I don't know, you would collect like NFTs or keep. It might just be pieces of information that travels from one shard to the other, from one contract to the other, and they help synchronize the state of a more complex dApp. And this is actually something that we're very actively researching. How do we split dApps into multiple shards, multiple contracts, so that people don't have to interact with a monolithic smart contract in one shard, but that they can have their own smart contract in their own shard, so everything goes a bit faster. Right, now I will go a little bit deeper. So this was an overview of the main challenges, of the main things we had to deal with. And now I'll go a little bit deeper into how we execute smart contracts. This is where it gets maybe a little more technical, but don't be scared. I'll try to explain everything in plain terms too. So first things first, from the get-go, we thought how cool it would be to have more than one VM. So what we did was we built a VM adapter, which allows plugging in any number of VMs. Basically, any piece of software that satisfies the interface can be a VM. But of course, VMs are not plug-and-play things; they're part of the consensus. So you need a system-wide upgrade to change the available VMs. However, this is possible. And even though right now we only have one VM, it's called R1, it's the Elrond VM. It has multiple versions. We had to do this to mitigate some of the backwards compatibility issues that we either had or might have had. So currently we use it for, it's a form of versioning so that older contracts can still run even if we change some of the VM characteristics. And of course, each smart contract points to its own VM. So each smart contract knows which VM it runs on. So it has a specific VM and VM version somewhere on the blockchain stored into it. But enough of that. Let's dive right into the Elrond VM, the R1 VM. So the story of this started actually in 2019. We had some attempts to port VM called the Yele VM to Elrond. This is formally specified dialect of LLVM, which is very cool. And we actually got it to work on the first testnet. We had a prototype of it, and we actually had a very, very cool game, which was called Crypto Bubbles. It was very addictive and made us spend a lot of time instead of working playing the game. I will admit that. Unfortunately, it's not online. It's not live anymore. But yeah, maybe we'll revive it at some point in the future. Who knows if there's enough demand for it. The only problem was this Yele VM. As cool as it was kind of slow. It was interpreter based. We couldn't get it to run more than a couple dozen transactions in a block, which was of a not very complex smart contract. So we figured it will be very, very difficult to scale like that. So sometime late 2019, we switched to WebAssembly and specifically to Wasmer. Now, we're at the WebAssembly conference, so everybody knows what WebAssembly is. We chose Wasmer and WebAssembly especially because it's very portable and it's very fast. And we tried to get it to be as fast as possible. We use single pass just-in-time compilations. So our contracts are stored as WebAssembly binaries on the blockchain. Whenever we have a transaction to a smart contract, it gets compiled. We also get the local caching of smart contract binaries. Since this just-in-time compilation can take quite a little bit of time, so we try to optimize this like this. We have configurable per opcode metering. We used a prototype actually, and what we're running on is actually a fork of Wasmer that has a few small modifications that we needed. And we also use runtime breakpoints, which we use, to get out with panics and stuff like that. Right. Another very important feature of it, it's the smart contracts run in a stateless sandbox. So they actually don't communicate directly with the blockchain. Of course, they can ask data from the protocol, like, what's the current block, stuff like that. But the results are never committed to the blockchain until the execution has finished successfully, which again helps a lot with reliability, and it also makes it a bit faster because it doesn't have to have such long-reaching communications within it. Now, this is This is the sandwich, our text sandwich, very, very simplified. So there on the bottom, you have the Elrond Go node. That is basically the main piece of software of the blockchain. That is the protocol. It does all the magic. It makes the blockchain exist. On top of it, we have the adapter that we talked about. This adapter allows connecting various VMs, which we have, I think, yeah, 1 or 2, as I mentioned before. On top, we have our Elrond VM, which is called R1. And this VM is, the main focus of my talk, actually. It runs an instance of Wasmer in it. And also it has something very interesting, which I'm going to dive a little bit deeper in the following few slides, which is called smart contract primitives, which is we offer some sort of standard library to smart contracts, and I'll explain in a moment why. And we also have a lot of execution contexts. These are all kinds of stuff like managing state, managing inputs, managing outputs, managing errors, and also very importantly, managing these calls between contracts, which can be asynchronous or synchronous. So there's a lot of magic, actually. There's a lot of code in it to ensure that correct communication between the shards, between the contracts can happen. On top of that, we have our smart contracts. And smart contracts, of course, they are WebAssembly contracts. So whenever we commit something to the blockchain, we commit a WebAssembly binary, that's it. But of course, we don't want to write directly WebAssembly by hand, although it is possible and it's okay to write. But for your everyday developers, you want to have a nice high-level language built on it. And the language that we've invested most in is Rust. We have a Rust framework that we've been working on for 1.5 years or 2, I think, which offers all kinds of features. You will see a small screenshot of it. We also offer very minimal C and C++ frameworks. Now, you can write smart contracts for Elrond in C and C++. We actually do it all the time, but we mostly do it for testing, to test our own framework, and not so much for general contract development. For that, we recommend Rust. Of course, in the future, we plan on expanding this list of languages, but yeah, that takes time, and it just made more sense to focus on one for now. Now, this is, again, a little bit more technical, but I think it's interesting how R1 and Wasmer interact, how the integration between the two works. So here on the left, you have the node, the blockchain. This feeds inputs into the VM. These inputs, they are basically transactions that the users send to the blockchain. Now, then R1 takes these inputs and it can do one of 2 things. If it's a new contract it doesn't know anything about, it will just send the Wasm contract bytecode to a single pass streaming compiler. This compiler will create an executable, and the executable will be run. Now, if R1 has seen this contract before, it loads it from the cache, so it goes faster than like this. And then the executable will run the smart contract. It also has metering injected into it, and then the contract has access to an environment. It's the environment interface, where we provide a multitude of methods that contracts can use to interact with the blockchain, like give me the arguments, these are my results, load something from storage, write something to storage, etc. We have loads of those. Okay, and now we'll go a bit deeper into what these kind of primitive, what this kind of this EI is for a smart contract. We actually provide quite a comprehensive library, basically baked into the VM. And the reason for this is we figured very soon along the way that smart contract size is critical. And it's critical for 2 reasons. Now, of course, we want to have as little data as we can in the blockchain. And of course, every smart contract is stored on the blockchain. So if we have a very big contract, this will inflate a lot the size of our blockchain, which we don't want, because we want people to be able to run nodes on machines that are as small as possible, make it as accessible to everyone. But there's another side to it. It's the fact that a lot of the times you have to compile these Wasm bytecodes to machine code, and this takes time. For a big contract, it might be 80 or 90% of your transactions. We don't want that. You want small, very, very small contracts, so the compilation is fast. Even with caching, you still want it to be as fast as possible. So we made ourselves this goal of having very, very small smart contracts, no larger than a few kilobytes in size, which we're every day struggling to get better at. We started, for instance, with certain contracts had 100 kilobytes, and we reduced them to maybe 30 or 40. We have also a few contracts that are smaller than 1 kilobyte inside. We have an ERC20, which we use for benchmarking, which we managed to reduce down to 3.5 kilobytes in size, which is very, very small. But how were we able to achieve this? And here comes the trick that we use. Now you could think of it as a precompile, although it's more like something baked directly into the framework. We have these mathematical and crypto operations that we offer for smart contracts to use directly from the VM. Now for crypto, it's pretty easy to understand. So a contract needs to call a crypto function. It just calls it from the VM. The VM gives out the result. But we did this for more than just crypto. We did it for mathematics too. So we have these kind of managed types, which mean that the VM actually keeps some data during the execution of a smart contract. And this data is usually large types that we wouldn't normally want to handle in the Wasm bytecode. So think of it as a sort of standard library. The idea is that we want smart contracts to only contain the business logic, very, very minimal, only only the what and not the how, and let the VM do everything else and in a very optimized manner. So how it works is the VM has this kind of heap, is a structure where you have a handle, and with a handle you get access to a number or a string of bytes. So the Wasm memory doesn't have to hold them. And these types are as follows. So our first type that we played around with was bigint. Now, of course, smart contracts work with balances, for instance. And on Elrond, the balances are not floating points, okay, because you want a comma, you want a decimal, but we don't use floating point because it would be too unstable. We use fixed point. And so basically, every time you send one eagle to somebody else in the blockchain, you're actually sending a 1 followed by 18 zeros of the smallest unit, which is, I don't know, a tiny eagled way or something. So from the get-go, even the most simple contracts need to work with really big numbers. So we thought, why not just bake a bigint library directly into the VM, since it's so fundamental to running all contracts, which we did. Now, there's another difference that is between EVM and what we did. EVM usually works a lot with 256-bit numbers. Problem is, from time to time, these overflow. Not often, but sometimes they overflow. And with bigint, you don't run that risk, basically, which made our life easier and helped us sleep at night a bit better. But yeah, again, baking bigint into each and every Wasm would have inflated them a lot, and it wouldn't have been so much worth it since everybody needs it anyway. And a few months ago, we also added a more general version of it, which are called managed buffers, which is just random strings of bytes. We use them for all kinds of stuff, to concatenate like error messages, to concatenate keys for storage, everything we do with them. We also have an elliptic curve object, which we use for cryptography, and we're developing a big float. So yeah, maybe in a month or two, if everything goes well, there will be access to big floats too in smart contracts. And I'll just go over on a very, very simple example of how a smart contract would work with this. This is actually what happens every day on our blockchain. So these numbers don't actually ever get loaded in Wasm. The contract never see them. It just tells the VM, hey, do this with these numbers. So this is a very simple example from a very simple contract. It's called an adder contract. It just has in storage a value, and then you can increment it. That's it. Very, very simple. But this value is a big int, so how would you go about it? The contract basically asks at the very beginning, the framework, hey, I'm expecting one argument, and this should be a big int. Just load this argument for me. And then the VM says, sure, okay, and here's your handle for it. This is handle 0. And the contract never sees the number, just gets the handle. Then, okay, I have this value in storage. Let's read this. And then the VM gives it the other value at handle 1. And the contract says, okay, sure, just add these two numbers together. And okay, the VM adds them behind the scenes and says, okay, so I'll put the result in handle 2. And then the contract says, save this to storage and maybe also return this. And you have a very, very small transaction, a small function that got executed. You managed to interact with the storage. You managed to receive arguments. You managed to deserialize them. You didn't have to worry about deserializing them or serializing them back. And you, during this entire time, the contract didn't see the numbers even once. It only told the VM what to do with them. So this is how we get really, really small, really small contracts. Okay, now here's some benchmarks. The latest one is the ERC20 benchmark. Now, again, we don't have ERC20s, but we use the ERC kind of smart contract for benchmark because it's so standard, because everybody knows how it looks like and what it does. So we managed to shrink it down to 3.5 kilobytes in size and half a millisecond per transfer. It's pretty fast. There will be more benchmarks. In the picture, we have a bit of an older comparison, but actually the Elrond numbers, we checked them this month. So the Elrond numbers are fresh. We don't know so much about the other ones, if they've changed or improved a lot. I don't know if we're the fastest or in the top, but I presume we're in the top. I hope that at some point we will have more comprehensive array of benchmarks that everybody can do, and so we can compare with each other. But that's not necessarily the point. The point is that it's fast and that it works. So there it goes. Now you might ask yourself, okay, but with all these managed numbers, isn't it very cumbersome to write smart contracts, because you have to work with these types which are not even in memory? And the answer is, well, yeah, it's not a problem, because we have high-level languages nowadays which are very powerful and can hide this complexity from you. And I'm talking about Rust. I have a lot of praise to say for Rust, because it is a very high-level language which allows you to express very high-level abstractions, but at the same time, it gives you a lot of capabilities to perform very, very low-level, very intense optimizations. So it's pretty amazing at that, and we tried to use it as much as we could, to use its magic as much as we could. And here we see an example of the smart contract I talked about earlier, the one with number there, which you can increment. And as you can see, nowhere do you have to specify, or you have to think of the fact that this big int type is actually not in memory, it's somewhere else. And you can even have operators on it, like run like plus, equals, stuff like that. And you don't care. In this whole example, you basically have deserialization of a big number. You have reading from storage, you have writing to storage, but you don't actually have to worry about it very much, because the framework does a lot for you. And actually, the most of the work that the framework does is at compile time, which means the actual smart contract output is small and very fast. And we're closing. We're closing the end, and it wouldn't be complete, this presentation, without talking a little bit about how we verify smart contracts, how we make sure that our infrastructure works okay, and how we verify that the contracts that developers build and that we also build run fine. And blockchain security and smart contract security is a thorny topic, to say the least. There's a lot of money being lost every week to software bugs. So we're not taking this lightly, quite the opposite. We've built an entire stack of tools that we use. Now, of course, first of all, we did some high-level stuff. So there's a component which is in Rust only that mocks everything, mocks the VM, mocks everything. But you can write unit tests and you can write integration tests in high-level Rust. And the cool thing is you get a debugger and you can get some high-level coverage, which we didn't yet manage to do running the WebAssembly. So everything you see at the first point that is not involving WebAssembly. So with everything mocked. Then the most important tool that we use for testing smart contracts is called Mandos. Mandos is a JSON format. It's you express basically in a JSON kind of way scenarios. So this is the blockchain. These are the contracts. These are the transactions, and these are the outputs that you expect. This is maybe the storage that you would expect after a transaction has happened. Yeah, by the way, in case you're wondering, Mandos is some character, some very little known character from Lord of the Rings. But anyway, that is beside the point. What is important is that it's not only a static language, so you don't only specify a smart contract scenario statically, but you can also integrate it with dynamic pieces of code. And actually, we figured out, I think a year ago, that no matter how many unit and integration tests we write, we're not going to cover everything. So we started building some fuzzers, and which was a great idea because we were able to much more aggressively test, and we discovered a lot of bugs like this. Not many, but the bugs that we found would have been very, very difficult to find otherwise. And the nice thing is that the fuzzers that we've built are actually integrated with Mandos. So they can use bits of pre-written scenarios, pre-written tests, and then mix and merge them. And then if something fails, then the fuzzer can also output a full scenario that they can run. You can make it part of your integration test suite. So this is quite nice, and we use it a lot. And then the last two things I want to talk about are based on our collaboration with Runtime Verification, which is a very cool company that does a lot of very cool products. Especially they do formal modeling of software, which is a very difficult but very, very rewarding field. And there's right now there's two projects we're running with them. They might get merged at some point. So one of them is a K-framework full implementation of our VM. Now, for those who don't know, K-framework is a framework that allows one to define languages in a formal way, and is very good at it. There's many technologies out there that allow people to define formal specifications, but K-framework is especially good at defining languages. They already had, so when we started, they already had an implementation of Wasm. So I think Ricard had a presentation about it 2 years ago at this very conference. Yeah, we're working with them to integrate that and also formally model the non-Wasm part of our VM. So the asynchronous calls and whatnot, bring them together and then run smart contracts using this this formally defined version of the VM. So this is executable, which means you can actually execute smart contracts on the K-framework implementation. But it's much more than that. You can also prove things about smart contracts. You can run all kinds of tools like coverage, fuzzers, all kinds of things, which is very cool. The other project that we have with them, we have our multi-sig contract. This is a contract that allows to have multiple signers on a transaction. And we had it modeled and verified also in K-framework. And its soundness was proven. I think the final output of this effort should come out this month or so. So it's actually very close to the end. And we also, it actually found some very subtle bugs. So I guess it was worth it. And we're also thinking about integrating the two. So that's also going to be something very interesting to look out for, to having very high level proofs about smart contracts, but also an executable sort of representation of everything that is going on the blockchain. So there we go. And we hope this will also be available for developers. Right now, it's still a bit experimental and a bit harder to use, but we're planning to release tools that are available for everyone. I'm sure I skipped over several things. Maybe I didn't cover quite everything. Maybe there's some places more in depth where I didn't go, but I'm actually open to a lot of questions, and yeah.